the idea of object-oriented programming. And if you look at human body or any creature, what you see in human bodies, we're composed of cells, right? Cells have cell membrane, and then they have a nucleus. So all interaction in a cell happens through the membrane, and nucleus is kind of this is like your own private stuff, which is not accessible to people outside, right? So these cells, they work together. He saw software as a living organism. And he says, okay, let's model the software the way a human body is. So we have these cells, which we call today as objects, right? And we have a public interface, which is what in biology is a cell membrane. And you interact with those cells, and you manipulate the state of that. So object-oriented programming actually was born that way. And then the language they created was called Smalltalk, and then there was another guy, Vijan Straustru. He was working on Unix kernel. So what he did was he liked Smalltalk, but he at AT&T, where Unix kernel was developed, they used to do C. So he took Smalltalk and C, and he married them together, and he created what they call as C++. It used to be called C with objects in 1979 or 1980, and then in 1983 they renamed it as C++. And C++, God forbids if you happen to have the chance to use it, is an overly complex language, right? Got really complex. And it was tied to the machine architecture because in 1980, right, there was no such thing called an internet. So there was no such thing called as an internet, there was no such thing as a web, everything, is machine oriented. But people were starting having problem because once you have internet, you cannot be very focused on a machine. For example, using a website, say google.com. Google.com is running on a server. Do you know what server that is? Is it a Windows server? Is it a Linux server? The very fact of an internet is that you have these independent computers which could use a different operating system, completely different system. They can talk in a language that's mutually understandable to each other. That's how internet is, right? C++ cannot do that. So C++ cannot do that. They wanted to create a new language because C++ cannot solve that problem. And that's how Java was born. So Java, which was renamed, which actually initially the version in Java, the language they call it was OAKS. And they were using it for embedded electronics. And suddenly the internet came and they said C++ cannot solve this problem. So let's use our new language, which we call as OAK, to solve this problem. And they renamed it as Java. And Java brought two things into the table. One, security, two, portability. And security and portability were both the needs of internet. Because until C++, when you run everything on your own program, you don't have any concept of security. I mean, you are the master of this, that's it. Like, nobody has access to it, so you're not worried about security. And you're also not worried about portability because let's say I have a Windows laptop. I need to run a software here. It has to run on Windows. I don't care whether it runs on Linux or a Mac. It has to run here, right? Whereas with internet, you have this concept that you have a Windows computer connected to a Linux computer connected to a Mac computer, and they're all different operating systems, different technology stacks. They have to talk to each other. So portability became a prime issue. So that's where Java came into the picture. The problem was Java was not very well suited to the problem of internet, but there was a whole lot of people who knew object-oriented programming. So they just, adapted the object-oriented programming and created Java, but later on they were like, there are better paradigms of thinking. And functional programming actually came into, the idea of functional programming was there long before, but it never picked up the mainstream because the problem with languages like Java is that they are great in solving small to medium problems, but as the software grows, they cannot really cope up with it. And the reason why they can't cope up with it is when you go back to the core of Java, right? You have an object, you have a private state. And as software grows, right, you have, let's say, initially few hundred classes, then they go into a few thousands of classes, then they go into a few millions of objects. And if you look at all the permutation combination of, I don't know if I'm able to explain it properly. I've never spoken to high school students, sorry. But the number of permutation and combinations that these objects can take is infinitely large. It's like really big. And when you look at bugs in software, what it is basically system enters into a state that it shouldn't enter, right? And that was the problem with object-oriented programming. And functional programming, and particularly F#, was born with the idea that the root of the problem is the concept of state, right? Because you have so many billions and billions of state combinations in an object-oriented programming language that it's not possible for a human to actually, kind of control or comprehend, and it leads to buggy software. So just remove the states, and that's where we come into that. Okay, so my name is Nikhil Bhartwal. I've worked as a professional engineer for about 10 years now. I've worked in all sorts of companies, big and small. I worked in Microsoft, Oracle, some of the startups. These days I'm in Bloomberg. Okay, so my background is more on microservices, cloud, and distributed systems, right? Functional programming was actually one of my hobby, and lately I worked with a startup called Jet.com. I don't know if you've heard of it. So there we actually used F# for pretty much web services. It was a big acquisition, like about $3 billion kind of stuff. But my exposure to F# actually happened during my time at Microsoft. So apart from work, I do give a lot of conferences and talks around the world. So that's my website. If you go there, it's a simple one. I just did it myself. But if you actually go around, you'll see a bunch of my talks. Okay. So I'll start. I've kept the level of the talk quite low, but if something is not clear, please interrupt me in the middle, right? So I'll start with what functional programming is, why do you want to use functional programming, F#, and a little bit of F# history. F# FYI is very well supported on Visual Studio, although you can run it on Linux and Mac also. I do a lot, there's no problem with that. Anyway, so let's start with what functional programming is, right? So functional programming is a programming paradigm, right? We just talked about dominating paradigms. You have the object-oriented languages like C++, Java. You have an imperative languages, C, Fortran, if someone has to use Pascal. When I was in high school, they used to teach a language called Pascal. I don't even know if anybody has heard of it, but it was actually a language that was back in the 80s, right? So it's been long. In those days, there was no such thing as a Java, right? So Pascal and C. Pascal was the language for students. So there's an imperative, there's a logic paradigm, and then there's a functional paradigm, right? We'll talk about what functional paradigm is in details, but the dominating characteristic of functional paradigm is that your data is immutable. What I mean to say by data is immutable is that in a language like Java, you assign a variable x equal to 5. You can change the value, right? X equal to 7, x equal to 8 throughout the execution. In a functional language, once you assign a variable to a value, you cannot change it. It's done. And the reason why it's designed the way it's designed is because this is the reason why you have bugs in the software, right? When you look at the famous blue screen on Windows code dump, or you see all those, bugs, what's happening is that your memory gets corrupted. And when you think about memory, what memory is memory is the state of your system. System enters into a state that you don't know how to recover, so it just crashes. So by making the data immutable, we prevent that state change. Now this is kind of bizarre for someone coming from Java. I mean, I can't change the value of the struct variable. How can I work? Turns out there is a way of doing it. You can successively apply functions to a value, and I'll show some examples that you actually can program. The second characteristic of a functional programming is that output depends on input. So you have a function y is equal to fx, right? In a typical language like Java, you have something called side effects. For example, you have a global variable somewhere. So you call some fx, but the y may not just depend on the input x, it might depend on global variables that you don't have access to right now. Right? So that is why it leads to kind of unpredictability. In a functional paradigm, what you have is whatever the output is strictly dependent on input. So in this case, y would only depend on x. Functions are the building blocks of functional programming. So you can combine these functions. I think Java 8, Java 9 does support limited amount of, I think they have a concept called lambda functions. I don't know, it's relatively recent, where you can do something like that. But functional programming basically says that you have your data that is immutable. So I assign some value and I just keep applying successive amounts of functions to transform the data rather than changing the value of the variable. That's how functional programming thinking works. And it's a declarative style of programming. A declarative style of programming means you tell what you want to do, not how you want to do it. So in Java, you have an algorithm, right? You write an algorithm for I is 1 to 2. You actually give, these are the steps you need to do in order to give me the result. In functional programming, it's more like, this is what I want. I'm not going to tell you how to do it. You do it yourself. But this is what I want. So declarative style of programming actually leads to a lot of efficiency. It's very easy to program. It's really productive. You can write big softwares using small lines of code. The only problem is sometimes you have to sacrifice a little bit on efficiency because the computer may not figure out the exact way how to do it or the best way. Humans can solve these problems at a smaller scale much more efficient than computer. Large scale computer would be better than humans. But anyhow, we'll see what declarative programming is. But before I go into details, I want to know why should you use functional programming, right? What's the use of it? So the first reason why you want to do it is that code is a lot more concise. I can write 100 lines of F# that can do the same job that 500 lines of Java can do. It's that much more efficient, literally. So imagine if you're running a company and instead of having 5 engineers, one person can do the work of 5. So the efficiency is huge because the code is very concise. It's a lot less bugs because state is the reason why you have bugs, right? So, am I making sense? Sorry, I don't want to shoot too much above people's head, right? Okay, so state is the reason why there are bugs, and by making the variables immutable, we have eliminated that state. It's very easy to understand to predict the behavior. The reason is that when you have a pure function, y is equal to fx, right? Your output only depends on input. Whereas there's nothing hidden behind. Whereas when you call a function or a method in Java's terminology of a class, you have these private variables of a class that might affect the output that you don't see immediately, right? So it leads to unpredictability. It's very easy to parallelize the code. And the reason why parallelization is basically ability to execute in parallel, right? You can do 5 things together. Most of the systems these days, if you look, they have like 2 or 4 processors. Each processor would have like 4 cores. Typically, you have like 16, 24 cores running on your systems today. Back when I was in high school, there used to be like 1 processor, 1 core, and that was running at like 1/10 the speed you have today. But parallelization is important. Parallelization is important because we, at current state, we have hit the level of technology where we cannot increase the speed of a chip. The reason is the chips are anyway very miniaturized, and at that point the chips heat a lot. So we can't really make the chip faster. But what we can do is we can make more chips. So that is why if you look at the trends today in computers, they'll have like multi-core processors because they can't increase the speed of a core, but they can have more than 1 core. That's why parallelization is very important. And this is the reason, easy to parallel, that functional programming now is more popular than it was 10, 20 years ago. 10, 20 years ago, languages like Java would do a good job because you don't really need to parallelize the code. And why it's easy to parallelize the code? Again, there is no state involved. If you have done multi-threaded programming in Java, then you use something horrible called threads, mutex, semaphores, and all those things. I hope you guys don't have to deal with it, but you probably would. It's pain, right? And functional programming eliminates all that. Okay, so let's see what functional programming is all about. Obviously, it's not magic. It only makes things easy that was hard before. All the all the problems that you have, you can solve it with Java. It's not like Java cannot do it. It's just that it takes you a lot more effort to do the same thing with Java. With F#, it would become a lot more easier. And it aims to let you write programs that are very easy, concise, bug-free, parallelized. We've discussed all that. So let's actually move to F#. How many of you know about .NET? Okay, some of you, good. So for those of you who don't know, let's look at the Java example first. So Java, we said Java is portable. Java runs on something called JVM, or Java Virtual Machine, right? And what it is, it's basically a layer between your hardware and your program that gives you the portability, right? It just translates your Java code into the machine code. So I have a Java program, I run it on a JVM on Windows. The JVM would translate what Java code does to the Windows specific API. I run the same program on Linux and Java. The JVM on Linux would take, my Java code and translate it to Linux calls. So JVM is that intermediate layer. It's a virtual machine that translates your application code into your operating system code, right? So JVM is one such virtual machine. It turns out there are actually two dominant ones. The other one is called .NET, and .NET is mostly, it's now open source, but it was what Microsoft created. And .NET used to be very Windows specific, but .NET used to be very Windows specific, but last 4 or 5 years they've actually open source. So now you can run .NET applications on your Mac and Linux. And F# basically is a language based on .NET. It's a mature cross-platform functional first programming language, which is to say that it's dominantly used for functional code paradigm, but you could, and there are reasons why you would want to do that, you could write object-oriented code or procedural code in F#. And it empowers the user to solve complex problems. It actually runs on .NET, and this is very important because there's a large number of libraries and third-party libraries for .NET. You can actually use F# and talk to those libraries. For example, let me again switch back to the Java example. In the Java world, there's a language called Scala, which is the functional language for Java. This is functional language for .NET. Scala is the functional language for Java. And you can write Scala code that can talk to your Java code. Because a lot of people have written libraries for Java, right? And you don't want to write everything from scratch. So I want to take the benefit of functional paradigm, but I don't want to reinvent the wheel. So I'm going to write my code in Java, but I can use Java library to run my code in Scala, but I can use Java libraries written by anybody else. So this lowers the barrier to adoption. F# can do the same thing, except F# can talk to all the languages in the .NET world. Most of the time it's actually going to be C#. So let's look at the origins of F#. So there was a functional language called OCaml. This was created in mid-70s, and it was basically used for mathematics and theorem proving. So they took this language and they took the .NET C# object-oriented language and they combined it to what they call as F#, right? And it has a characteristic. It's declarative style, it's immutability, functions as a building block. We'll see examples of all of them. But before that, why should we use F#? Well, if you start with F# as a multi-paradigm language, I can use it for functional, I can use it for object-oriented, I can use it for imperative. It runs on top of .NET platform. I already explained what .NET is. This is a little bit hard to get, but there is a concept called type inference. So in Java, you have types, right? You have integer, string, whatever your classes. Types are important in languages because types, basically, when your programs are very big, types would prevent a lot of bugs from getting in. But the problem with typing is that you have to type them, right? So type inference says that looking at your program, I can automatically figure out what your type is. So types are there, you just don't have to program them. So as a programmer, it makes my task easy because it's less typing for me. So it's cross-platform. On Unix, on Linux, Mac, Mono is there. Microsoft has its own version called .NET Core, so you can use F# on any platform. Fantastic IDE and tool support. I know somebody mentioned Visual Studio. I could actually show you Visual Studio F#, but it has fantastic IDEs. So we talked about declarative style. All right. So let's actually go into what declarative style is. Describe your problem, whereas prescriptive is describe the steps to solve your problem. So this is C#, right? You're writing loops and all those things, and you actually describe. Whereas in F#, you just say, for all the customers, I only want the customers who are VIP. So that's a descriptive. Just describe your problem, and it solves it. Here you have an algorithm in place that actually does it. So that's what a declarative style does. Immutability. I mentioned that once you assign a variable, you cannot change a name. So in C#, let's say you have var x equal to 1 and you say F#. They're not the same, because in C# you can do that. In F# you can't. Once you assign a variable, you cannot change the name. You can create a new variable that says y is equal to fx, but you can't change. There is an option, if you want to change, you can declare a variable as mutable. So you explicitly mark it, I want to change this variable, and this is the one that helps you prevent a lot of bugs. So functions as first-class values. What do I mean by that? This is what makes functional programming functional, right? I can create functions and I can treat them as variables. So I can store functions in a list, right? If you look at let operations, this is a list. We'll see what list is in detail, but it's basically a collection. Think of it right now as an array, it's not an array. And you see these increment, square, cube, they're actually functions. So I have defined 3 functions and I've created a list of these functions. I can assign a variable to point to a function. So right now, square is a function that takes an input x and gives you answer x process, which is basically x squared. So I can play around with functions. So I can take these functions and I can just twist and turn them any way. So what function programming basically does, it says define a data that is immutable, define these functions, and basically combine these functions and mix and match them in any way, and apply to that data and get the output. And what makes functional programming really very does is that you can combine these functions in such a way that you don't really have to basically repeat yourself. Whereas in object-oriented, there's a lot of boilerplate code that you write that makes your program lengthy. So you can so right now in this one, this is a function apply twice. And what apply twice does is it takes a function and a variable in input and applies that function twice. So I can pass this function as an argument to a function. I can return a function. So I basically create a function that takes an integer and increments it by a certain number. So this is the output value. The question is, if I can't change a variable, what about loops? I mean, if you look at loops and question.
Wait, so can you go back to the previous? Can you explain the though and after? Yeah. Can you explain the x equals and int equals?
This or this?
Well, both.
Okay. So apply twice takes a function that takes an integer and applies an integer. This is the type of the function, right? And takes a value. I'm not declaring the type because type inference can automatically. And say, I'm going to create a value that will apply this function x, right? Once to this value, and then I'm going to apply this function twice, the second time, to this value. So what I'm doing is I'm doing f of x. That's what apply twice is. Take any function, take any input, apply it twice, right? So what I'm trying to demonstrate is I'm taking function as an input. Here I'm doing the opposite. I'm returning a function to you. It says I'm going to create a function that takes an integer and gives you back a function that takes an integer to an integer. And what this function actually does, it takes an integer and it adds whatever integer you're giving it to. So here I'm returning, this is a function that is returning another function, right? This is a function that is accepting another function. Functions and variables have no difference in functional programming because variables is a special case of functions where if you have a function with 0 parameter, it becomes a variable. So functions and variables are kind of treated the same way. Make sense? Okay. So what about loops? I mean, you have all these loops, you loop through. Because I can't change a value once I assign to a variable, I can't have this code as it is. So now I have to change it, and I say list.iter. So you can basically have this value and apply this function to this list, right? This list.iter is basically a function that takes this function and a list and applies that to each one, right? So this is an example of what I'm going to call as higher order function, right? You're taking a function as an input, so that's a loop. Same thing, I have this. I can do something like, I'm going to create I as an array of this one. List iter, do something on I. So what about when I have to return a value? So this is a common Java code you have, let's say you're doing like Fibonacci numbers or summing a list. So you have like initial sum is 0, some condition, I just iterate over them, do something, change something. Here I'm defining a recursive function. Recursive function is a function that calls itself with a different value. Recursion exists in Java also. So your basically loops can get translated to recursive function. I say I'm defining a function I that does something and then takes this value and calls itself. So you have a recursion, and my return value basically I is apply this function with the initial number, and you get the final output. So here I'm not mutating a variable. And the compiler is pretty smart. So internally the compiler would translate this code into that code internally. Questions? Okay. So we have talked about function. How about storing data? Okay. So we have tuples. We'll see tuples are basically a collection of types, but you can mix and match types in tuples. I'll show you some examples. Records. In the Java world, these are, in the C++ world, these are structs. In the Java world, you would call them as data classes, in the sense classes that don't have any methods. And then you have discriminated union. This is a little bit tricky and a very functional stuff. But we'll look at each one of them in detail. So this is like a tuple. This is C#, by the way, not F#. So tuple is basically a collection, in this case, of integer and an integer. It's a pair, right? A pair doesn't mean two values. I can have a pair of 3, 4, 5 collection. So that's a tuple, right? For example, I divide two integers. I have a divisor and I have a remainder, right? Quotient and remainder. That's what. So this is how it gets translated in F#. This is how a tuple in F# would look like, quotient and remainder. That's C# and that's the equivalent F#. Same thing, you have the C# here, and I can just assign this tuple directly. So quotient comma remainder is divide. This is a function. I call this function with values 10 and 3. In this case, the quotient will become 3 and the remainder will become 1. So that's a tuple. So let's look at records now. Next. Something. Oops. Yeah. Another example is success value. I can try parse. So let's say I'm trying to parse an integer, right? If you give me a valid integer, in case 42, I can have success as true and value is 42 in this case. Now if you give me blah 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 here, the success will be false and value could be undefined. Doesn't matter, because I'm trying to parse and I couldn't parse. So this is how you can basically return whether operation is successful or not. So record. A typical record in F#, a record is basically a collection. Again, they don't have to be of the same type, right? It could be quotient, remainder, examples. The difference between a tuple and a record is that records has name to those variables. Now, if you observe tuple, I mean, you might call it as quotient and this one, but from a system's point of view, it's just two integers. Which one is quotient, which one is remainder, makes no difference. Whereas records basically attach a name. So there's a quotient, there's a remainder. When you assign a quotient as this, remainder as this. Okay. Once you have a record, you have to define all the fields. So you can't just say quotient is 3 and I don't tell you what the remainder is. This is going to be an error. So now you can define new result that says, well, quotient is the same, but the remainder is 0. Right? You could do that. You could say the same thing in this way. This is just an alternative notation. And you need all this because you can't change a variable, right? So you assign a record, you need to change it. The defining characteristic, and this is something different about Java with C++ and C# and all those languages, is that when you compare two classes, let's say you compare two string and you say A is equal to B, even if those string contains the same value, they will still not be the same. Java would say false. And the reason why Java says false is because internally, every class is a pointer to the location in memory. So when you compare a string, right, and say string A is equal to Nikhil, string B is equal to Bertwal, A equal to B, it basically compares the pointer to A and pointer to B. And even if, in this case, the value is different, but even if the value is same, let's say A is equal to Nikhil, B is equal to Nikhil, A equal to B, they are pointing to different string, will give false. Structural equality says that when you give me a comparison, I actually look at the contents and not the memory location, right? Contents of the data and tell you whether it's same. So now you have two different variables, two different memory locations with the same contents. So F#, C# would say yes. If the same code was run in Java, it would say false, because from Java's point of view, it says result 1 is a different location in memory than result 2. So in string comparison in Java, you actually have to do something like A dot equals B. That's where it actually does structural comparison. Otherwise, it just compares pointers. F# does structural all the time. Discriminated unions, that's a little bit of a tricky thing, but we'll look at it. This is C# code, but Java would have something similar, right? You basically have like an expression, or you basically have, my data could be of this form or that form set of choices. I can define the same as something like expression could be of this. Discriminated union is essentially a collection of record, and you're saying your data could be of one or the other one, right? So I could be of either one of them. I can't be both, but I can, or all of them, or combination. I have to be one of them. I could be add, I could be subtract. So imagine you're writing a compiler, you're writing a mathematics expression, right? Add two numbers, subtract two numbers. So you can use these discriminated unions there. In Java, C# world, you actually have to have a big class hierarchy. And then you can pattern match. So I could say I want to evaluate this expression. If it's add, I do like e plus 1 equal to subtract, I do subtract, divide, multiply, whatever. So F# has this feature called pattern matching on these discriminated unions. So this is an example of a function definition, right? You have this function generate, you have all of these nested functions, you have these max, we'll talk about these piping operators later on. And then you have match, and you can match. If this is null, then don't do anything. If it's fill up with character and so on, and then you have for loops, which does certain operation and returns a value. So that's how a function would look like. This is the main function generate, and you have separate functions. These are called inline functions separately. C# I think allows that. I believe the new versions of Java would allow you to do inline functions, the old ones don't. So anyway, this is how a function definition would look like. So these are the types, right? Now we've talked about types, we've talked about integers, strings, all those things. In F#, types can be really complicated because types don't only represent the values, they represent the function. So this says, give me an integer, I'll give you back an integer. This is of the type int to int, and it's actually a function, right? This is all the same. Give me two integers, add x and y, and I'll give you a third one. This is, I don't need anything, I need some generic type. And unit means I don't give you an output. It's like a void, Java void function, right? Console read line says, I don't need anything input, but I'll give you back an output. So this is like when you read line, you don't pass an input, but you actually get an output. Sum means give me a list of something and I'll give you the total. Filter means give me a function that takes some item x, this is generic programming, right? Gives me a boolean and a list, and I'm going to apply this filter and give you a list that satisfies all these conditions. And same thing with map. Give me a list of A, give me a function from A to B, and I can apply these functions successively and give you a list of type B. So these are definitions and these are the functions. So we talk about higher order functions, right? The hallmark of functional programming is that you can mix and match these functions anyway. So functions are input parameters, partial applications. I'll give you examples of all of them. Compositions. So so I have this function. We already saw an example. I can take an input. I can do an output. So on. So higher order functions basically means I can combine these simple functions and I can create more complex functions out of it. One example is partial application. So I have a sum function, right? A plus b, simple. Then I say, I'm going to apply it partially. So this is the result, sum 1, 2, it will give you basically 3, simple. But instead of this, I can apply it partially. So I can say, I will give you one parameter, but I won't give you another parameter. So what this does to you, it actually creates another function, which is a specialization of sum, that all it does is takes one value and applies one. Let's see what happens next. So now I'm creating another function called add1. This creates a function that takes an integer and returns an output, which is basically 1 plus the input. Same thing here, doing the same thing. And now I can do a result and I can say add 1 to 2 and it returns 3. So see, I've taken this one function and instead of giving all the parameters a, b, I just give partial parameters and I create sub-functions, right? So this is partial applications. I've created some functions and I've created sub-functions from it. And you can do the same thing, add 1, it will give you answer 4, right? When you do an add 1, what it does is, it says add 1 is basically sum 1, so it substitutes sum 1 here, sum 1, 3, and the answer will be 4. So partial application is one way to create functions from other functions. Other one is compositions. So what compositions are? I know add 1 is this function, add 2 is this function. I can create a third function that says apply add 1 first, and then apply add 2. So I take two functions and I fuse them together that the output of one function becomes the input of another function. So add 3. Great. Returns 4. Okay. Piping operator. I saw some examples of piping operator, but I didn't really describe them. So this is what a piping operator is. In functional programming, you're not changing the input, right? What you're doing is successive operations of applications of functions on an input. So you have x, you can apply it successively h of g of x, so you can write it this way. This actually is a very handy way of writing stuff. So I can just say something like filtered number is a filter. Let's say you have numbers 1, 2, 3, 4. I can just say, okay, I'm applying this function where I'm going to filter all of those for all those n that are greater than 1. So I can have this written as this, and there are a lot of practical applications for this kind of programming. For example, if you're writing your own programming language, if you're looking at compilers, so what is a compiler doing? A compiler takes your C++ or Java code and it outputs a machine code. What it is doing is it's successively applying functions to your input, right? I take your Java code, I lex and parse, create an abstract tree, then I do some optimization and output. You're basically passing it through different stages. There's a paradigm called railway-oriented programming which actually does the same thing. But that's pipelining operator. All right? So you can apply any number of filters, any number of maps, and so on. Very, very handy, makes your code very readable. Options. What is an option? There are a lot of cases where, let's say, you perform some operation on input, and in some cases you get a valid answer, in some cases you don't. For example, I'm giving you an array. I want you to find a position of a particular element. So I'm giving you an array 1, 2, 3, 4, 5, 6, and I give you a number 3 and I say, give me the position of number 3 in that array. So you can say, well, it's the third position. Now what if I give you a number 20 in this array 1, 2, 3, 4, 5, 6? Obviously 20 doesn't exist, so there's no value. So for certain operations, you have a value and sometimes you don't have a value. So there's a type called option, like there's a value or there is nothing. So I can have something like this is a valid integer, this is an invalid integer, and then I can match it. If it's a valid integer, print it. If it's not a valid integer, don't print it. Options are really handy. There's a horrible thing in Java called null. Probably you might not have used it if you don't create your data structures. That is actually a source of big bugs. And some people call null as the biggest misinfection or the biggest mistake in the history of programming languages. Its null pointer exception is like, you have an object, but it doesn't exist and it returns a null. So options basically were created to reduce these nulls. I don't know if you've created your data structures in Java, but if you do, you probably should be using a lot of null there. Collection, talk about data structures now. You have arrays, typical Java arrays, you have a list, right? List is immutable. Java's I can mutate. And then you have a sequence called lazy list. And what lazy list is lazy list will compute the values only when you actually call, not otherwise. And lazy lists are very useful in, let's say, communication. You're doing, let's say you're writing something like communicating with the satellite, right? There's a lot of operations fetching the data from the satellite. So you say, if I need it, I will call you, but if I don't need it, don't compute it before. So that's the difference between lazy list and, let's say, something like array or list. Array or list is what they call as eager evaluation. The moment you say A is equal to 1, 2, 3, 4, it evaluates it. Lazy list, when you say B is equal to some ABC value, let's say functions F1, F2, F3, it doesn't really evaluate it. It will only evaluate it when you need it. So for optimization and IO operations, sequences are used quite a lot. Arrays, you have the standard array example, right? I can reference them, I can create them. Arrays are always mutable. You have list of numbers. I can combine these lists, create them anyway. They are immutable once I do odd numbers. Give me all the numbers from 1 to 1000, stepping 2 at a time, or to 0. These are generators. I can use these generators, and then I can apply filters and maps. So I can do all these operations, right? Give me all the VIPs and then just just give me their name. Sequences. We talked about sequences. They are basically lazy lists. Same thing as list, except they are not computed. They are only computed on demand, and that's where the word lazy comes in. Lazy means I don't do work unless you really push me to do it. That's where the term lazy comes in. Object-oriented programming. So we are going into classes. I think I'm running out of time, so I'm going to go a little fast. So this is a C# class. This is an F# class, right? Type something. These are the members, properties, mutable fields. So you have the F# classes. This is the F#, C# and F#, right? Mutable, wherever you want the values to be changed, you mark it explicitly mutable. Interfaces. In Java, they have interface. Yeah, they have an interface. Yeah, that's a C# interface. There's an F# interface. You have abstract members there, right? That's F# classes. And finally, you have some excellent resources to learn F#. These are wonderful websites. There are books. This guy, Don Syme, he's the inventor of F#. And you have some real-world functional programming. F# for people who want to learn from C#. Beginning F#, F#3, this is also a very nice book. Things like functional programming, I mean, they, when you go into, probably you might not do it at high school, but when you go into web services, think of something like Google. They are processing like millions and millions of requests per second, right? These things are used there. Now, if you're writing a small project, you could potentially write it in F#, but you can also do it in Java. It's not going to be a lot of difference. So all that I've talked about, the code is parallelable, easy to fix. At that level, you think about these issues. And that is where all this would come handy. In fact, at MIT, some time back, they used to teach a programming language called Lisp, which is a very early programming language from 1950s actually, as their first introductory language. I think they have switched to Python. But MIT used to do it because they teach you a lot of these fundamental aspects of communication. Because when you go into computations, when you go into object-oriented language, you get tied too much into machine and registers and so on. So that's it. I'm up for questions. Yes.
How does a language like F# compare to a language like MATLAB or R or a similar functional programming language?
Good questions. Conceptually, they are similar. The difference is F# is a general purpose language, whereas MATLAB is not a general purpose language, right? So the design goal of MATLAB is that they should be easy to use for scientists and programmers who don't want to learn a lot of programming, right? So they abstract out a lot of these issues like performance and memory management for you, because an engineer who has to solve multiply through metrics, I don't want to understand how memory is allocated and deallocated. Right? So MATLAB would try to simplify things for you. F# being a general purpose language, right, and designed for someone like a power user, right? As a computer scientist, often when you build large-scale distributed systems, you have to do a lot of trade-offs. So F# would have a lot more. It's obviously more complicated to use than F#. It would have a lot of these choices that you have to make, a lot of different data structures, a lot of different options that you make a decision. And they will support a lot of third-party graphics library, I/O libraries that MATLAB doesn't have to do it, because in MATLAB, all you're doing is, what graphics would you need? You probably would be doing some plotting. That's probably it, right? You're not going to create a next version of Microsoft Office in MATLAB. You would do it in F#. That's where the difference would come. Yes, sir.
You mentioned like OCaml and C++, oh no, C#. C# used to make F#. You mentioned a lot about like how C# is similar to F# as how is OCaml similar to F#, because I'm very familiar with OCaml.
Oh, good, excellent. You're the first guy who knows OCaml. Anyway, the core of the language. So, if you remove the object-oriented part, and I mean, if you're familiar with OCaml, you would have seen all the syntax examples very similar to OCaml. Basically, they adapted OCaml for .NET. That's what they did. So the core of the language was very similar, right? The difference came in when they had to add the object-oriented layer to OCaml. Because the thing with OCaml is it gets translated to binary code. Whereas F#, the design goal of F# is it has to interoperate with .NET languages, right? So it has to use the same object-oriented mechanism that C# use, otherwise they won't be able to talk to each other. The very reason why you have F# is because I can interact with a whole lot of .NET libraries, right? So at the object-oriented level, F# would be different. But if you look at the original specifications of F#, if you look at F#2, F#3, OCaml and F#, they would look the same. The module system in OCaml would be different from F#. OCaml has functors, which F# does not have. F# on their end would have sequences don't exist in OCaml, right? List and arrays, they would be the similar. Also in OCaml, the syntax for discriminated unions, if you notice, you don't really have tags, right? I can have expression integer into integer, something like that. Whereas F#, the F#4 actually adds these. So F# and OCaml were very similar languages until 2008, 2009. And it's actually tragic that OCaml community, they are not very active and they don't really actively that much develop the language. But F# actually evolved. But until that point, the core of the language, if you remove all the object-oriented features, would be the same. Also, the multi-threading model for OCaml and F# would be very different. For OCaml, they actually don't really have a very good multi-threading. Because OCaml was built as a single, even their garbage collection mechanism, everything is single-threaded. Whereas F# would use a different multi-threading model. Again, the difference between OCaml and F# mostly would boil down to OCaml gets translated to the machine code, F# gets translated to .NET bytecode. That's where the difference would come. Okay, next question.
So from my understanding, if I have a large production environment handling multiple requests per second, I do something like F#. So I develop my web server using F#, and I'm assuming F# has a library which can connect to databases like MongoDB or MySQL.
Oh yeah. They would have everything. There's a, I don't have configured internet, but you could, first of all, don't think of F# libraries, think of them as .NET libraries. Because libraries could be in C# also, it doesn't matter to you, right? It's the same thing as if I'm using Scala in Java, you're using a JVM library.
Yeah.
It doesn't matter whether that library is written in Java, Scala, or Clojure. To say that whether .NET has it, absolutely. I mean, .NET is a competitor to Java, they would have pretty much everything that Java would have. If you go and program into something like Azure, Azure is by nature being a Microsoft product, would have .NET bindings for everything. Even Amazon and Google Cloud would support substantial, so you would have like everything. They may not be F sharp, they may be C sharp libraries, but it wouldn't matter to you.
So the relationship between .NET and C Sharp is like between Python and C almost? Would that be
no, I
a
think
fair comparison?
Python is a bad example because
I
it's a
know, because of
dynamic
the
language.
performance.
But relation between .NET and C sharp or .NET and F sharp is the same as between Java and JVM. That's a fair comparison.
Oh, okay. Right. Yeah.
Yes.
Thank
Like,
you.
what is F sharp most commonly used for?
In theory, F sharp can be used for everything. But mostly it's used for data science. Actually, functional paradigm is very well suited for mathematical oriented programming, right? Like you mentioned MATLAB, but MATLAB was too specific for case, but data science where you're doing a lot of, like, for example, Microsoft would have a lot of speech recognition software on your Windows Phone, iPhone, Cortana, everything written mostly in F sharp. So data science finds a very big F sharp. There are microservices written in F sharp. These are the common use cases, but again, from a language point of view, being a general purpose language, can I use F sharp to write another version of Microsoft Office? Of course I can do that. Nothing stops me. Questions? More questions? Okay, thank you.